All right, so we're just continuing a little bit with double integrals in volume. So I'm going to ask you guys a few questions. So we are solving a problem, and we get these two possible equivalent solutions. Here's one. And we know that that is equal to this other solution that we come up with. Which one are we going to choose to work with, and why?
Is that in the second one, because we don't know how to take the derivative of that one, but we can just put an x in front of it.
So Emily says we want to work with the second one because we don't, to integrate sine y squared dy, we don't know how to do that. But if we do this one first, we integrate sine y squared with respect to x, we just end up with an x in front of it because it's constant with respect to x. And then when we evaluate, we end up with a 2y and we get a u sub integral, so that's easy. So that was a quick one to recognize. If we had to do this, if we had to come up with some value for this first integral, sine y squared dy, how could we do it? We have the tools.
Mr. Mayor, can you use u sub
For the first one?
Yeah.
We don't have because we have a y squared here, we don't have a du.
Is that one of your things in the back of the book?
There's a good one. How about look it up in the back of the book, look it up in a table. Would be a good technique. There's probably something back there. Anybody else have another idea? What's that? Wolfram alpha? Okay. How about an approximation? Is there something we could... What kind of series? What do we have? A Taylor series for sine x. Substitute a y squared in. And so we have a Taylor series expansion for sine y squared. And we could pick a few terms of that and integrate 3 terms. And you just have polynomials and evaluate those. So you'd have an approximation to your integral. So no, I just wanted you guys to think about it. Just think about the tools that we have available. So if we had to do this, we could use a Taylor series, and it would turn out we would just be integrating polynomials, and we'd have an approximation to our integral. All right, so you guys were quick on that one. Second question: R, we have a region. R is a region in the xy plane. And the area of R equals B. F of xy equals a constant on R. What is the double integral over the region of f of xy dA? A? Which A is what?
Well,
B. What?
BK.
Okay, Ann says BK. Why, Ann?
Because you just substitute.
So let's think about it a little more. If f, you're on the right track. If f of xy equals k, what is that telling us? What is that function over the region? What does it look like? It's a plane. and it equals f of xy equals k, so how high is it above the xy plane?
Okay.
K. So it's a plane parallel to the xy plane at a height k. What is this? What's that? So on that region it's flat. So on that region we could think of it as a plane above the xy plane, that little piece of it. And what is the integral, what is the double integral over the region f of xy dA? What does that give us? The volume. So if our height is constant and the region, the area of the region is B, what's going to be the volume of that region? BK, the area of the base times the height. So that's going to be B times K. So we didn't even have to integrate. All right, those are my first two initials. The third one, my last question to you. This one you have to evaluate. 0 to natural log 10, e to the x 10,
Is that natural log y?
yes. All right, so we're evaluating this.
Can we just rewrite it so we can do like dx dy?
So we want to change the order,
Yeah.
because do we know how to evaluate? Do we know how to do natural log 1 over natural log y dy, the integral of that? No. So let's change our order. So that's our first step, change order. So we need to figure out what our region looks like. So our region in the xy plane. Y goes from e to the x to 10. So here's e to the x, here's 10. So my original integral, my rectangles are this way. X is going to be x equals natural log 10. So if I switch my rectangles and I go this way, so we'll rewrite this integral. So we get the integral, x goes from 0 to natural log 10. Y goes from 1 to 10. Good. 1 over natural log y dx dy. Now you should be able to do this one quickly. You should be able to do this one in your head. You're almost there, Scott. Plug in your limits.
Oh, it's like a change of base thing.
No, it's even easier than that.
Is natural log a 0, 1?
Oh, we made a mistake here, didn't we? On our limit. Y goes from, or sorry, x goes from 0 to, not natural log of 10. And if that, in terms of y, natural log y. Now do it.
Okay.
Okay, that's easier.
Now it's 9.
Equals 9. Because when we evaluate this integral, we just get the integral of natural log of y over natural log of y, which is 1. So we just get the integral of dy from 1 to 10, which is just 10 minus 1, which is 9. So we go from something that's impossible to something that we can do in our head. All right. Any questions on double integrals and volume? Our homework tonight is just some more double integrals with volume. I love double integrals. And when we do triple integrals, that's even more fun.
What? Oh, we're gonna have to switch triple integrals around. Is it possible to do that?
Yeah,
Is it in
yeah.
X, Y, and Z?
X, Y, and Z. Usually, triple integrals are nice because you can do cylindrical coordinates or spherical coordinates. And if your shape is curved, and doing triple integrals in spherical coordinates is so nice. Because your limits end up being like 0 to pi over 2, 0 to pi, and 0 to 1, or something like that, because of your shape. So I came across, I was reading an article in a journal that I subscribe to, Mathematics Magazine, all about Pascal's triangle. And I thought this was just an interesting little...
So we don't really need to know this part.
You don't really need to know this part.
So you can just watch for it.
You can watch for entertainment and edification. So you guys are, I'm sure you're familiar with Pascal's triangle. I'll just draw out a few rows.
Coefficients of the degrees of the polynomial.
Right. All right, so these are the first several rows, and usually we call this the 0 row. So we're just going to give these rows numbers. So these are the coefficients. They're the binomial coefficients. So if you expand x plus a squared, x plus a to the third, these are the coefficients. You may have also heard, it's pretty well known that if you sum the rows, that the sum is 2 to the n, where these are the n's. So the sum of the rows is 2 to the n. If we just add all these numbers up, we get 2 to the n for these n's. But what I'm interested in, what the article talked about, was if you do the product of the rows. So I'm going to make a chart, and we'll look at the product of the rows. So for this column, we'll do n, and we're going to do the product here. And we're going to see if we can find a relationship in the product, or we will find a relationship in the product. What's that? I did. So we'll start, I'll just do this. And then we'll do, I'm going to go do a dot, dot, dot to 1,000. And if we do the product of the 0 row, our product is 1. The product of the second row is, for n equals 1 is 1. For n equals 2, we get 2. For n equals 3, we get 9. For this, we get 96. For this, we get 2,500. For n equals 6, we get 1, 6, 2, 0, 0, 0. And you'll have to take my word for it on the 1,000, and I took the word of the person who wrote the article because I didn't want to calculate it. It's about 1.68 times 10 to the 215,681. So this grows, the product of the rows grows very quickly. So to look at it, to look at how quickly it grows, we're going to do the ratio of the products. So the ratio of the the next product with the previous product. So our ratio here is 1. Our ratio here is 1. Here we get 4.5. Here we get 10.667. Here we get 64.8. Here we get, whoops, I skipped one. Here we get 26.042. And here we get 40 or 64.8. And we go dot, 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 and our ratio here is, again, I had to take somebody's word for it, is 2.49 times 10 to the 432nd. So this grows pretty quickly. So let's look at the ratio of the ratios. So we start out here at 2. Here we get 2.25. Here we get 2.370. Here we get 2.441. Here we get 2.448. Dot, dot, dot. We get 2.71692. Anybody recognize this?
Oh, it's
E. The limit, as we take the ratio of the ratios, is E.
What is that?
It's just interesting.
It doesn't.
And if you write out the formal expression for the product of the rows and do the ratio and the ratio of the ratios, you can prove that that the limit, you end up with 1 plus 1 over n to the n as n is approaching infinity.
Is that where E came from?
This is E. E actually originally came from calculating continuously compounded interest. Were making tables of continuously compounded interest, and they saw that this thing kept coming up. So anyway, I looked at this and I'd never heard this, and I thought that was kind of interesting.
So someone did this proof?
Yeah.
for it?